So this is a recording for the lecture for the first half of section 10.1, in which we're going to investigate comparing two different proportions. By the time we're done with this first lecture, we should learn how to create and interpret a confidence interval which involves two separate samples from two distinct populations and perform some sort of inference on them. Before we get into the procedure, we need to back up and talk about some of the stuff that's going to underlie this procedure. And this procedure is going to be based on a couple of things. One, our knowledge of the distribution of sample proportions. And two, what happens when we take one random variable and subtract it by another random variable and look at the distribution of that difference of random variables. So where we start is, imagine we have two distinct populations. Let's call them population one and population two. And we have some parameter of interest we'll call P1 and P2. Now, we know that um, uh, we can't easily do a census for these two different populations. So imagine instead we do separate samples from population one and population two. And in the process of doing that, we end up with two samples. They may not be of different, they may be of different size, and each one of them produces um, a sample statistic. Now, where we want to talk about is like, imagine if we did this repeatedly, getting a different p hat 1 and a different p hat 2, subtracting the two, and putting that on some sort of plot. Again, do another sample of size n1, do another size from population 1, do a sample of size n2 from population 2. Each time we do this, we create those two different p hats, subtract the two, plot it. What is what does the distribution of the difference between these two proportions look like? Well, we know that with each single sample, we know that let's say for p hat 1, that the distribution is approximately normal as long as we get at least 10 successes and 10 failures. We know that the center of that distribution will be the same as the population proportion. And we also know that the standard deviation of the p hat is the square root of p1 minus p over n, as long as the 10% condition has been met, which guarantees independence. So let's try to make this a little bit more real. Imagine that we have two high schools, school one, school two. And somehow we know that at school one, 70% of the kids did their homework last night. At school two, somehow we know that 50% of those students did their homework last night. Now, imagine that from school one, we do a simple random sample of 100. Just stop right there. Forget about the next part. Just 100 students, right? What would the sample distribution of p hat 1 look like in this case? Well, do we expect at least 10 successes and failures? We do. Um, do we expect it to be centered at 0.7, the population proportion? We do. And can we calculate the standard deviation of that distribution? Well, there we have it right there. Square root 0.7 times 0.3 over 100. So we have about a 5% standard deviation for that distribution. Okay, now imagine from school two, we take a random sample of 200. Okay, well, what if we did many samples of size 200? What would we expect from that sampling distribution? Well, we would expect that it's going to be centered at its population proportion, 50. Do we expect the distribution to be approximately normal? Well, with 200 students and 50% of them doing their homework, do we expect at least 10 successes and 10 failures? We do. And then lastly, can we calculate the spread for that situation? Sure. Square root of zero point 0.5 times zero point 0.5 divided by 200, or about 3.5% for standard deviation. Now, last piece. What if we chose randomly something from this group, randomly something from this group, found their difference, and then mapped it? And we did this repeatedly. What kind of shape do we expect? Well, we found out before that if you look at the difference between two random variables, the distribution of two random variables, we know that if both distributions are random, if both distributions are approximately normal, so will this sampling distribution of the difference of those random variables. So we're not surprised when we look at these differences that the shape is approximately normal. We expect that when we look at the distribution of two random variables, that the mean of the difference of those two random variables will be the difference in the means themselves. Well, 0.7 minus 0.5, 0.2. We are not surprised that the center of that difference of proportions is 0.2. And then lastly, what about the spread? Well, we may recall that when we do differences of random variables, that the variance of that difference of random variables is equal to the sums of the variances of the individuals. Or in this case, we may say, hey, the variance of p hat 1 minus p hat 2 is going to equal to the variance of p hat 1, which is the standard deviation squared, plus the variance, of p hat 2, which is that squared. And then if you want to get rid of that square, you could take the square root of that. And if we did that, we would find that that's very close to what that number is. So, in summary, the sampling distribution of the difference of proportions is the foundation from which we're going to be doing some inference later. We know that the shape of the distribution is approximately normal. We know that the center of the distribution should be equal to the differences in the population proportions from those two different populations. And then lastly, that the standard deviation of the difference of proportions can be found using this formula. This formula, by the way, is found on the formula sheets, as long as we meet the 10% condition for both of those cases. Remember, if we want to say that the shape is approximately normal, we need to check to make sure that the individual distributions are also approximately normal. Turning the page. So there's our shape of the distribution of p hat 1 minus p hat 2. Let's take a look at an example and see if we can get the feeling for this particular distribution. It says, suppose we have two large high schools, each with more than 2,000 students in a certain town. At school one, 70% of the students did their homework last night. Only 50% at school two did their homework last night. Counselor school one takes a simple random sample of 100 students and records the proportion P1, P hat 1. School 2's counselor does a sample of 200 students and gets a P hat 2. They meet together and they find that the difference in these proportions is 10%. Is that a strange outcome? Well, let's see if we can figure that out. First of all, let's talk about the distribution from which that 10% comes. The distribution of the difference of p hats. Shape. Well, if we want to talk about the shape, we would first say, do we expect that the distribution of p hat 1 to be normal. Or if I sample 100 from that population with a population proportion of 70 percent, I expect to see 70 successes. That's greater than or equal to 10. And 1 times 1 minus p hat, or p1, is 100 times 70. I expected 30 failures. That looks pretty good. I think the sampling distribution of p hat 1 is approximately normal. N2 p2 is 200 times 50, which is 100. And that 100 is greater than or equal to 10. N2, 1 minus P2 is 200. And again, times 0.5, it's still 100. And that 100 is still greater than 10. So because both of the sampling distributions of p hats are approximately normal, the distribution of p hat 1 minus p hat 2 is approximately normal. Okay, what about the center? Well, we talked about the fact that the mean of p hat 1 minus p hat 2 would be the same as the mean of p hat 1 minus the mean of p hat 2, which we know these two values are both p1 and p2. So in this case, we expect that the difference between p hat 1 and p hat 2 over many, many trials is going to be 0.2. You can see that reflected there. And then what about the spread? Again, using the formula, the standard deviation of p hat 1 minus p hat 2 is equal to the square root of 0.7 times 0.3 over 100. That is, it is p1, 1 minus p1 over n1, plus 0.5 times 0.5 over 200, which of course again is p2, 1 minus p2 over n2. And what value is that? Well, let's break out our calculator and let's do that calculation. Whoops, I want a new program. Menu, add the calculator. There we go. I want to take the square root, control division, and I'm going to do 0.7 times 0.3, and that's going to be divided by my sample size of 100, and then 0.5 times 0.5, all divided by 200. So the standard deviation of the differences is going to be 0.0579. All right? So we know all about this distribution. Now, how unusual is it that we'd have a difference of 10 or more extreme? Well, one way to do this would be to say, well, look at that point 10. How far is that from what we expected? We expected about 20. We got 10. Well, we could calculate the z value for that. 0.1 minus 0.2. There's our differences in the observed value and the mean, divided by 0.579. And if I go to my calculator, 0.1 minus 0.2 divided by, and I'll just type in 0.0579, and we get a z value of negative 1.73. What's the probability that a z value would be less than negative 173? Well, for that, we could use the norm CDF function on our calculator, and that would be negative infinity to negative 713, mean of 0, standard deviation of 1. And that menu, let's see, it's under probability, distributions, normal CDF, negative infinity to negative 1.73, and the other values are fine. So about 4%, 4.18%. Okay. Given that, oh, I guess what we just did there would have gone right there in our notes. And we would say in the last part, does the result give us reason to doubt the counselor's reported values? Well, let's just think about that. I might say, if the counselors were telling the truth, we would get a difference in proportion of 0.1 only well, maybe I'll change it to a percentage, 4.18% of the time. And as we've seen in the past, this low probability makes us suspicious. So maybe because of that low probability, we doubt that they're telling the truth. All right. Let's do another example. Oh, in this example, we have two counselors, Julie and Michelle, and they are from the same school. Each of them did a random sample of 100 students and recorded the proportion of students who did their homework last night. When they finished, they found that their difference is 8%. They're surprised that the difference is this big, considering they're sampling from the same population. Is this a rare occurrence? Well, let's see if we can find that out. Let's start with talking about the shape from which their data came. Well, first of all, N1 maybe I really should write this down as NMPM, which was the 100 that Michelle got from. And they're both from school one, where there's 70% compliance. So 70 is the expected number of successes. It's greater than or equal to 10. And Michelle, 1 minus, probably for Michelle's sample, 0.3. And again, we get 30. 30 is greater than or equal to 10. And we'll do the same thing with Julie. And we're not surprised, as all the numbers are the same, that her distribution also meets our criteria for being normal. So p hat Michelle minus p hat Julie is approximately normal. Okay, what about the center? Well, the center of p hat Michelle minus p hat Julie will be 0.7 minus 0.7, which is 0. Meaning that if they were to do these samples repeatedly and kept on subtracting their two sample proportions, that sometimes Michelle's number is going to be a little bit bigger, sometimes Julie's number is going to be a little bit bigger, but over many, many trials, the average difference in these proportions is 0. And then what about the spread? Well, as we said before, the standard deviation of the difference in these two proportions is going to be 0.7 times 0.3 over 100, 0.7 times 0.3 over 100. And suppose we should get out the calculator again and find out what value that is. So control square root, control fraction, 0.7 times 0.3, and that's all divided by 100. And then we'll add to that same fraction, 0.7 times 0.3 all over 100. And we get that standard deviation is 0.0648. All right, so we know about the center and spread. Now, what's the probability that the two will be 0.8 apart? Well, let's just map this out a little bit. All right, I've got a normal distribution centered at 0 with a standard deviation of about 6%, 6.5%. So one standard deviation up, 0.065, another standard deviation, about to 13, negative 0.065, and negative 0.13. And here we are being 8 apart. Well, 8% is about this and that part of it. Oh, wait, we could also be 8 apart in this direction. They don't say whether Michelle's or whether Julie's is the bigger one. So those two tails end up being the probability that we're interested in finding out. Now, because of the symmetry, those two tails could be found by multiplying by 2 the norm CDF of 0.08 to infinity with the mean of 0 and the standard deviation of 0.0648. And if I put that in my calculator, menu, probability distributions, norm CDF, and I'm going to go 0.08, and my upper bound is infinity, so I'll hit that infinity button, and our mean is 0, and our standard deviation is 0.0648. Enter, enter. Oh, I probably should have said, by the way, lower, upper, mean, and standard deviation. But we get this number 0.216070. Okay, so there's our probability of that happening. Are we surprised to get such a big difference? And the answer is a difference of 0.08 occurs by chance about 22% of the time. So therefore, this result occurrence is therefore not surprising. All right. So now that we've got all this background work done, what are we going to use it for? Well, what we're going to use it for, as we scoot past the homework, is talk about using the fact that we know about the sampling distribution of p hat 1 minus p hat 2 to calculate confidence intervals. Now, we already know a bit about confidence intervals, that it's makes a range of values that we think the true parameter would exist. Um, in this case, we have a, a statistic. Well, we had a statistic before, but our statistic now is going to be the difference between the two sample proportions that we see. Distribution is still normal, so we're still going to use Z star. Now, in the examples we've done, we have been using this formula for the samples for the standard deviation of the difference of p hat 1 and p hat 2. But there's a problem. All those times we did that, it assumed that we actually knew what p hat 1 and p hat 2 were. Now, it ends up that we don't. You know, when they said 70% of the kids did the homework, we really didn't know that. We were just kind of guessing it. So what we need to do, because we don't know what P1 is, we don't know what P2 is we make a reasonable guess. What is our reasonable guess? Our reasonable guess is that instead of P1, we're going to use P hat 1. And instead of P2, we're going to use P hat 2. And because we've made this change using statistics instead of parameters for that calculation, we call this a standard error as compared to a standard deviation. And the standard error is what we're going to use in our confidence interval calculation. Pulling it all together, we have this formula, p hat 1 minus p hat 2 plus or minus z star times the square root. That makes up that standard error. But remember, we can only do this if we meet our conditions. Our samples better come from two random samples from two distinct populations. Our normal condition, we better make sure that both P1 and P2, P hat 1 and P hat 2, are suggested to be normal distributions. That is, we should expect at least 10 successes and 10 failures from each of those different samples. And then lastly, we need to make sure that we're independent, that both samples are independent of each other and that we meet the 10% condition. So the two samples are independent and we meet the 10% condition. Let's see all of this in action. We're going to do a confidence interval 4-step problem. It says, as part of the Pew Internet and American Life project, researchers conducted 2 surveys in late 2009. The first survey asked a random sample of 800 US teens about their use of social media and the internet. A second survey posed similar questions to a random sample of 2,253 US adults. In each of these studies, 73%. In these 2 studies, 73% of teens and 47% of adults said they use social networking sites. Use these results to construct and interpret a 95% confidence interval for the difference between the proportions of all teens and adults who use social networking sites. So let's start out. Our first step is always about populations. So in this case, we have population 1, which is going to be US teens. And population 2, because we did 2 distinct samples, will be of US adults. What were we studying about them? Or in other words, what is our parameter of interest? It is the proportion that, what did they say? Use social networking sites. And that completes our first step. On the planning side, we need to name our procedure. We need to say, what is our method? And our method is called a two sample, because we have two distinct samples, Z interval or difference in population proportion. Our conditions, our first condition is random. And we say it is stated that we have two random samples. Give ourselves a check mark for those two random samples. Second condition is that we have independence. And in this case, N1, which was 800, is certainly less than 1/10 of the population of all US teens. And that N2, which was 2,253, is certainly less than 1/10 of all US adults. We can pretty safely say that there are at least 22,053 or 22,530 US adults. And then lastly, our normal condition. N1 times P1. Well, we don't know what P1 is. So really, we'll have to take a best guess, and that's going to be P hat 1, which is going to be 800 times 73%. Now, I'm going to break out the calculator on this. And we're going to find out that 800 times 73% ends up being 584. And that number is certainly greater than or equal to 10. N1 times 1 minus P hat 1 is 800 times 27, because 73 minus, or 100% minus 73% is 27%. Find out that value, 800 times 127, and we get 216, and that number is certainly greater than 10. So we're halfway through the normal condition check. Check it out for the adults. N2 times P hat 2, 2,253 times 47%. So when we do this calculation, we don't get a whole number. But what we'll do is we'll round to the nearest whole number. And that'll be handy for later on when we use the built-in program for calculating these inference procedures. And our last one, 2257 times 53%, 2253 times 53%. And we get, again, a number which we will round to the nearest whole number. And that number is also greater than or equal to 10. We have now checked and we've seen that it meets all of the conditions for our procedure. Let's go to the calculation step. Remember, our general formula is that it is P hat 1 minus P hat 2 plus or minus Z star times the square root of P hat 1 1 minus p hat 1 over n1 plus p hat 2, 1 minus p hat 2 over n2. And in this case, this is 73% minus 47%. There's our difference in proportions, plus or minus z star. And let's double check. They want a 95% confidence interval. So we know that z star value very well. That is 1.96 times 0.73 times 0.37 over 800 plus 0.47 times 0.53 over 2253. Let's put that in our calculator. 0.73 minus 0.47 minus 1.96 times square root of the fraction 0.73 times 0.3. Oh, misspoke. That's not 37. That's 27. Ooh, 7 over 800. And then 0.47 times 0.53 all over 2253. Okay, that looks okay. And we get as our lower bound 0.22, and it rounds to 30. And then let's go ahead and adjust this for doing the upper end, changing that minus to a plus sign, and we get 0.2970. All right, there's the end of our calculation step. Now the interpretation, and that is with 95% confidence, we believe the difference in the true proportion of US teens. There's our reference to our population. That, what was our thing? Use social networking. And so the difference between this true proportion and the true proportion of US adults who, or that, use social networking is between 0.2230 and 0.2970. Now, something I just kind of want to bring out here is I don't think we're surprised that the difference that teens use social networking more. This thing says not only do we know that they use it more, but we know that they use it more by somewhere in the 20%. We would not be surprised to hear that teens use social networking 25% more than adults do. It gives us a range of values that we think the true difference sits in. Let's do one more example. Right? Again, looking at survey from this Pew Internet study. right? Are teens and are teens or adults more likely to go online daily? Pew Internet and American Life Project, that's a random sample of 800 teens and a separate random sample of adults, how often they use the internet. In the two surveys, 63% of the teens and 68% of adults said they go online every day. Constructed interpret a 90% confidence interval for the difference in the sample proportions. Okay, so once again, population. Number one, US teens. Population. Number two, US adults. Parameter of interest. And we're interested in both groups, the proportion that go online every day. So describe the populations that we want to compare and how we're measuring them. What's our plan? Again, our method is called the two sample Z interval for difference in population proportion. For our random condition, two random samples allows us to say we meet that condition. For our independence condition is N1, 800, less than 1/10 of the population of all US teens. Yeah, we think there's at least 8,000 US teens. Is N2, which is 2053, is that less than 1/10? Big N2. Do we think there's at least 22,530 US adults? Quite clearly. For a normal condition, N1 P hat 1, which is 800 times. And in this case, we said 63% of teens said they went online every day. Let's break out our calculator and make that calculation. 800 times 63%. And that's 504, which is greater than or equal to 10. We get a check mark there. N1, 1 minus P hat 1. That would be 800 times 37%. And that is 296, which is also greater than or equal to 10. N2 P hat 2 is the 2053 times the 68% of adults in that survey that said that they go online daily. And that number, 1,532.04, round to the nearest person. It's greater than or equal to 10. N2, 1 minus P hat 2, 2253 times 32%. And that number comes in at 721. And we meet that conditions. All right. Let's go to the calculation step. Confidence interval is going to be that 63% minus the 68%, teens minus adults, plus or minus the Z star And in this case, because it's a 90% confidence interval, we're going to use 1.645 times the square root of 63 times 37% over 800 plus 68% times 32% over the 2,553. So let's go ahead and get that in. 0.63 minus 0.68 minus 1.645 times square root of, now we need a fraction, 0.63 times 0.37 divided by 800, and then add to that a second fraction, 0.68 times 0.32 over 2053. Our lower bound for our confidence interval is negative 0.0824. Now, are you concerned that it's negative? I'm not, because I knew that there were less teens than adults in this particular survey. And so the difference could be negative because the proportion for adults is larger. Okay, let's get the high end. And that high end, I'm going to go ahead and change the minus sign by the critical value, the plus sign, and we get negative 0.176. And we're ready to interpret that in the context of our problem, and that is with 90% confidence, we believe, not know, we believe the difference in the true proportion of US teens, because it's our first group, that, what do we measure about them? Go online every day. And I'm just repeating the words from the problem stem. And the true proportion of US adults who, or that, go online every day is between, and we repeat our numbers from above, negative 0.0827 and negative 0.176. Now, last comment here. All of the values in this confidence interval are negative. There isn't the possibility, or sorry, one of the values that is not plausible is 0. Is not plausible given this particular data that the proportion for the teens and the proportion for the adults is the same. And this is an idea that we're going to revisit when we talk about doing significance tests with two sample population proportions.